we're looking at Chapter 6, Exponential Functions. Specifically, we're looking at Chapter 6, Section 6.2. In this lesson, we'll look at identifying characteristics of exponential functions from its equation. So we'll be looking for increasing and decreasing functions, the maximum possible number of x-intercepts, the y-intercept, domain, range, and end behavior. Last section, in Section 6.1, we investigated the graphs. Now we're going to look specifically at the equations. Let's just recall quickly from the polynomial functions we studied in Chapter 5. We're going to look at similar characteristics like the number of x-intercepts, y-intercepts, end behavior, domain, and range. We had 4 polynomial functions we looked at in Chapter 5, constant, a linear, quadratic, cubic. We looked at the number of x-intercepts, and we looked at the end behavior. The line extends from quadrant 2 to quadrant 1, for example. The domain of all of the polynomial functions we looked at in Chapter 5 was x such that x belongs to a set of reals. And so we had various domain or ranges. We're going to continue looking at these characteristics now for exponential functions. So recall that an exponential function is a function of the form f of x equals a times b to the power of x, where a cannot equal 0 and b must be positive. For an increasing function, the base b will be greater than 1. For a decreasing function, the base will be between 0 and 1. If we look at an increasing function, we see it increases here, and we know that it's an increasing function since 5 is the base, which is greater than 1. Here the y-intercept would be 2. We can see that in the table. When x equals 0, the y-intercept would be 2. So g of 0 is 2, and that's our y-intercept. If we look at the next table of values, also 10 is the base, which is greater than 1, which gives us an increasing function. And the y-intercept of this one, when f of 0 would be equal to 1. Let's have a look at decreasing exponential functions. And we see here the base is 1/2. Of course, that's between 0 and 1. And hence we have a decreasing exponential function. If we look at h of 0, because when x is 0, we find the y-intercept. That would be 1. And there's a 1 here in the a place. We're looking at another decreasing function. Here the base will be 1/4. 1/4 is between 0 and 1, so that's how we know it's a decreasing function. The y-intercept in this case would be 8, and let's just verify j of 0. When x is 0, we have the y-intercept being 8. So we're looking at an equation. The y-intercept will always be a. So in this case, we have the y-intercept being 1. Here, we have the y-intercept being 2, the y-intercept being 1 again, and the y-intercept being 8. So we have to keep in mind, we can look at an equation and tell whether it's decreasing or increasing from the b, the base, or the y-intercept, which is a. Let's have a look at an example. This example, since 5/2 is greater than 1, this will give us an increasing function. So we have an increasing function. The number of x-intercepts of this exponential function would be 0. The y-intercept would be 3. And of course, since it's an increasing function, it would look something like this. It goes from quadrant 2 to quadrant 1. The domain, as with any exponential function, is x belongs to a set of real numbers. And the range is y is greater than 0. Y belongs to a set of real numbers. If we look at the next one, next example, 2/3 is our base. And so 2/3 is greater than 0, but less than 1. So that gives us a decreasing function. If we were asked to find f of 2, and we replace x with 2, and f of 2 would be equal to 3 side of 2/3 to the power of 2, which would give us 3 side of 4/9. And this would give us 4/3. So f of 2 would equal 4/3. The number of x-intercepts here would be 0. The y-intercept would be 3 again. In behavior is quadrant 2 to quadrant 1. The domain, x belongs to a set of real numbers. In the range, y is greater than 0. Will not be equal to 0 since there are no x-intercepts. We have y is greater than 0. Y belongs to a set of real numbers. Sorry. If we look at the next example, we're going to determine an exponential function that is used to model a table of values. We have to be able to look at the table of values and determine the function, the exponential function that defines it. So here we see that in this case, we have when x is 0, a is going to equal 1, so our y-intercept is 1. To determine the base, we see that 2 divided by 1 will give us 2. 4 divided by 2 will give us 2. 8 divided by 4, it increases by a factor of 2. And so that will give us b equal to 2. And so our exponential function would be 2 to the power of x, since 1 is our y-intercept. If we look at the next function, I can tell that as x increases, y decreases. So it must be a decreasing function. If I look at when x equals 0, that tells me that a equals 64. It's not the first value in the table that we use for the y-intercept. It's when x equals 0. To determine the ratio, our b value, I see that 64 over 256 would give me 0.25. 0.25, which I could tell that b is 1/4. So we have f of x is equal to 64 out of 1/4 to the power of x. Let's look at an example where we're matching equations to the graphs. So when we're matching equations to the graphs, there's two things we consider. We consider the base, so we can determine if something's decreasing or increasing, and we look at the y-intercept. So in this case, we have an increasing and an increasing, a decreasing and a decreasing. So if we look at the increasing functions first, we have the first one with a y-intercept of 1. So our increasing functions is b and c, and we have b has a y-intercept of 1, where c has a y-intercept of something less than 1. So we know that y equals 3 to the power of x is b. And since this one is now used, and this is the only, graph c is the only increasing function left, we see that y equals 1/3, 3 to the power of x would be this function. It makes sense for the y-intercept to be 1/3 here. So we have decreasing functions left. Now we must look at the y-intercepts. We have a y-intercept of 3, which is this one right here. So this would be y equals 3 out of 1/3 x. And here we would have y equals 1/3 x. You may want to pause the clip and have a look at this example on your own. I'm going to continue. Once again, I'm going to investigate increasing and decreasing first. I have an decreasing, an increasing, a decreasing, and an increasing. So I'm going to look at this graph as an increasing function with the y-intercept 2. So I have an increasing function with the y-intercept 4, and I have an increasing function with the y-intercept 2. So I know that the first graph would be y equals 2, 4 to the power of x. In my next function, function b, I also have an increasing function. I have an increasing function where the y-intercept is 4. Here we have an increasing function where the y-intercept is 4. And so, this function would be y equals 3 to the power of x. I have two decreasing functions left. Here I have a decreasing function where the y-intercept is 3, and I have a decreasing function where the y-intercept is 4. So we have the y-intercept 3 and the y-intercept 4. So this would be y equals 3 0.2 to the power of x. This one would be y equals 4 0.5 to the power of x. We'll just have a look at a summary. And we'll do a few examples in this table. If you look at a function, we're going to have a look at the first function, y equals 9 times 7 to the power of x. Here, the y-intercept would be 9. The base is 7, which tells me that that would be an increasing function since 7 is greater than 1. The domain will be x belongs to a set of real numbers, and the range is y is greater than 0, where y belongs to a set of real numbers. If I look then down at example C, I have a y-intercept of 6. The base is 1/7, which, because that is between 0 and 1, is a decreasing function. The domain will be x belongs to a set of real numbers, and the range is y is greater than 0, where y belongs to a set of real numbers. I'll look then right at the last example of E. We have a y-intercept of 2, and the base is the irrational number e. Here, this will be an increasing function, since e is greater than 1. The domain will be x belongs to a set of real numbers, and the range will be y is greater than 0, or y belongs to a set of real numbers. For D, we have the y-intercept of 2. The base is 0.35, which gives us a decreasing function since that's less than 1 but greater than 0. The domain will be x belongs to a set of real numbers, and the range is y is greater than 0. Y belongs to a set of real numbers. In the last example, we have the y-intercept being 7, the base being 4. Since 4 is greater than 1, that's an increasing function. The domain will be x belongs to a set of real numbers, and the range will be y is greater than 0. Y belongs to a set of real numbers. The end behavior for all of these functions would be from quadrant 2 to quadrant 1.